It begins in a place that barely counts as a place at all. No galaxies, no stars, no light, no darkness. Just a newborn universe suspended between becoming and not yet existing, perfectly smooth, perfectly uniform, perfectly symmetric. A fraction of a second after the Big Bang, everything is so evenly distributed that there is no direction to prefer, no feature that stands out, no imbalance to hint at future structure. If you could drift through that primordial moment, you wouldn't see swirling gases or the glow of forming stars. You would see nothing in particular, a cosmic stillness that borders on the abstract, a universe that hasn't yet decided what it wants to be. It's strange to imagine that the universe, so full of motion and complexity today, began in a state with almost none. The earliest instants were governed by energies so high that the forces we treat as distinct, electromagnetism, the weak force, maybe even the strong force, were unified. Their separate identities had not yet emerged. Matter and radiation were in equilibrium. Space itself was expanding at a rate so extreme it makes the speed of light feel domesticated. And yet, for all this intensity, everything remained symmetric, perfectly balanced. In physics, symmetry isn't just an aesthetic notion, it's a mathematical one. A system is symmetric if you can transform it, rotate it, translate it, flip it in some way, and nothing about its fundamental description changes. The laws remain the same. The particles behave the same. The fields that fill space don't prefer one state over another. Symmetry is order in its purest, most uncompromising form. But symmetry has a cost. It's featureless. In a perfectly symmetric universe, nothing distinguishes one point from another. Nothing evolves into something else. There's no contrast, no gradients, no tiny variations that allow gravity to take hold and start assembling the architecture of galaxies. Absolute symmetry is elegant but sterile. It's like a blank sheet of music, mathematically perfect but silent. And so the earliest universe existed in a kind of paradoxical beauty, stunningly harmonious, yet containing no structures, no patterns, nothing recognizable, just a smooth ocean of energy and possibility. As you drift through that uniformity, picture it not as empty, but as filled with fields, continuous entities that stretch through every point in space. Physicists think these fields governed everything from particle masses to the forces we experience today. In those first moments, the fields rested at perfect symmetry points, balanced atop peaks of potential energy, in configurations where every possible direction was the same. The universe was like a pencil standing perfectly upright on its tip. Theoretically possible, practically impossible to sustain. And here, the philosophical tension begins to emerge. We often imagine perfection as a kind of ultimate state, something orderly, stable, serene. But the cosmos seems to reject that version of perfection. Perfect symmetry leaves no room for form, texture, or individuality. A universe that stays perfectly symmetric would never evolve stars, or chemistry, or life. It might not evolve anything. It would simply expand as a featureless, undifferentiated medium forever. Meaning, in a cosmic sense, requires contrast. For anything to stand out, symmetry must be broken. Yet the universe began with symmetry. Why? One answer comes from field theory. High-energy conditions naturally restore symmetry. Just as heating a magnet to a high enough temperature erases its orientation, the early universe was too energetic for distinctions to exist. Everything was washed into homogeneity. Only as the cosmos expanded and cooled could hidden tendencies begin to emerge. But that explanation addresses how symmetry was restored, not why it eventually shattered. The deeper question remains: why did the universe allow imperfection at all? It might help to imagine that early universe state as unstable equilibrium. Perfect symmetry wasn't the natural resting place. It was a temporary one. The fields filling the cosmos sat atop those metaphorical peaks, and when cooling nudged them, they rolled into lower energy states. But crucially, there wasn't just one direction in which to roll. There were countless possibilities, each equally valid. Once the symmetry broke, the universe chose one configuration out of many. That choice, whether in the Higgs field, in the separation of fundamental forces, or in tiny fluctuations sown by quantum randomness, became the fingerprint of our cosmos. Here is the cinematic irony. The universe didn't break symmetry once. It broke it again and again and again. Each time, the break produced structure. The first distinctions between forces, the first differences between particles, the first density variations in the primordial plasma. These imperfections were subtle, almost trivial, yet they cascaded into consequences so enormous we measure them in billions of light years. In a perfectly symmetric universe, matter and antimatter would have been produced in identical amounts and annihilated into pure radiation. No atoms, no stars, no carbon, no life wondering what symmetry ever meant. Something had to tip the scales. Some imbalance, some betrayal of symmetry had to favour matter ever so slightly. And it did. But that's a story waiting ahead. For now, in this opening moment, we hover in the calm before imperfection. The smooth early universe doesn't reveal what it's about to become. It doesn't hint that galaxies will someday swirl with tens of billions of stars, or that planets will eventually cool, or that molecules on a quiet world will someday evolve minds capable of asking why symmetry matters at all. Before we go deeper, if you enjoy exploring the quiet wonders of the cosmos like this, consider subscribing and leaving a comment with where you're listening from and what time it is there. It helps this channel grow and it keeps these journeys alive. As the universe expands in this imagining, quantum fluctuations flicker, minuscule, transient variations born from the uncertainty built into nature itself. They seem harmless, mere statistical noise, but even these tiny variations represent cracks in symmetry, the seeds of future galaxies. Stretching under the violent expansion of inflation, these fluctuations imprint themselves onto space like faint ripples. Imperfection begins to take root, and so the universe leaves its perfectly balanced childhood behind. The smoothness fades. The fields begin to shift. Symmetry starts to tremble. The cosmic pencil wobbles, and somewhere, quietly, inevitably, it falls. You don't notice the consequences yet. There is no sound of breaking, no flash of light, no cosmic announcement. Symmetry breaking is subtle, but it is the first domino in a long chain that turns the universe from a placid field of potential into a sprawling, structure-rich cosmos. In that moment, the universe stops being perfect and starts being interesting. The calm uniformity of the early universe is deceptive. Inside that smoothness lies an ocean of energy so dense and so hot that no particle, no force, no interaction behaves the way it does today. The cosmos is only microseconds old, and its temperature sits above 1 trillion degrees, far beyond anything achievable on Earth, even in the most ambitious particle accelerators. Matter exists, not as atoms or even nuclei, but as a seething, opaque plasma of quarks and gluons, an unbound storm of the very ingredients that will one day form protons, neutrons, and ultimately every element that fills the periodic table. If you drift through this infant universe, you would not see particles moving as familiar objects. You would feel the intensity of energy itself, fields interacting with each other in states we can barely describe mathematically, unified at scales where distinctions dissolve. At these temperatures, the strong force, the weak force, and electromagnetism do not behave as separate entities. Their differences blur. The interactions that later shape chemistry and stellar fusion are suspended in a higher symmetry, but the universe cannot stay like this. Cooling, driven by relentless expansion, begins to reshape the rules of physics. As the universe expands, its temperature drops, and the fields permeating space start to respond. Some shift into new configurations, others stabilize. A few become trapped in metastable states like supercooled liquids waiting for a nudge to crystallize. Physical laws, as fundamental as they seem, are not fixed at birth. They emerge step by step, each change triggered by a phase transition. To imagine these cosmic transitions, think of familiar substances on Earth: water freezing into ice, metal becoming magnetic as it cools below a certain temperature, a superconductor suddenly losing all electrical resistance when the right conditions are met. Each of these transitions is governed by symmetry. Above a critical temperature, a system can look perfectly symmetric, its internal patterns hidden by thermal chaos. Below that temperature, the symmetry breaks, revealing structure. The early universe experienced changes like these, but on scales vastly beyond anything in our terrestrial world. Instead of water molecules aligning into crystalline patterns, it was the fundamental fields of nature aligning into the laws we know today. Instead of a magnet choosing a direction of north and south, the Higgs field chose a particular value, giving mass to particles that had previously been massless. Instead of tiny droplets forming in a cooling vapor, quantum fluctuations seeded the structure of future galaxies. Each phase transition carried consequences that rippled outward across billions of years. At around a microsecond old, the universe cools enough for quarks to bind into protons and neutrons. Before this point, the strong nuclear force was too overwhelmed by heat to confine anything. Particles were ripped apart faster than they could come together. But as temperatures drop below roughly 2 trillion degrees, confinement becomes possible. It's the equivalent of vapor condensing into liquid, but on a subatomic scale. The universe transitions from a free quark-gluon plasma into a hadronic phase, where matter begins to resemble something stable. This is not merely a chemical change, it's a structural one. With protons and neutrons now able to exist, the ingredients for nuclei emerge. Yet the universe is still too hot to allow them to bind for long. Every attempt at forming light nuclei is undone by the next collision. It's like trying to stack blocks on a vibrating table. Structure constantly forms and dissolves. Cooling continues. At about 1 second after the Big Bang, temperatures fall to around 10 billion degrees, and the weak nuclear force begins to decouple from the cosmic plasma. Neutrinos, previously trapped in constant collisions, are suddenly free to drift through space unimpeded. This decoupling is itself a phase transition, as the behavior of one of the fundamental forces changes dramatically. Neutrinos become cosmic archaeologists, forever carrying information from this era. A few minutes later, around the time the universe reaches 1 billion degrees, another transition takes place: primordial nucleosynthesis. Now protons and neutrons can finally bind into light nuclei: helium, deuterium, traces of lithium. The laws of nuclear physics that we know today only make sense because the universe passed through this cooling threshold. Had the cooling rate been slightly different, or the balance between protons and neutrons altered, the cosmic recipe for chemical structure would have changed. What's easy to miss is that all these transitions depend on symmetry breaking, fields shifting, particles acquiring mass, forces separating. When we look at modern condensed matter physics, superconductivity, superfluidity, magnetization, we find striking analogies. In a sense, your refrigerator, your stove, your metal tools all reenact the early universe's behavior when they undergo phase transitions. It's one of the most elegant connections in modern physics, the idea that understanding boiling water or liquid helium helps us decode the nature of the cosmos. During the earliest fractions of a second, before the phase transitions we can reproduce in laboratories, the universe underwent even more profound transformations. The electroweak force, for example, behaved as a single unified interaction at high energy. Only when the temperature fell below a critical threshold did the Higgs field settle into a non-zero value, splitting the force into its electromagnetic and weak components. This transition fundamentally changed the behavior of particles, creating mass where none existed before. It was not merely a shift in the properties of matter, it was a change in what matter is allowed to be. What makes these transitions so mesmerizing is that they involved choices, not conscious ones of course, but physical ones. fields that were once perfectly symmetric had to pick one state among many equivalent options. In condensed matter physics, a magnetic material cooling below its critical temperature will choose a random direction for its magnetic orientation. In the universe, fields made similar choices, selecting configurations that became permanent features of the cosmos. Some physicists speculate that if these fields had chosen differently, if the symmetry had broken in another direction, the universe might have been governed by different constants, different particles, maybe even different forces. In that hypothetical universe, chemistry as we know it might not exist. Stars might behave differently. Life might be impossible. All of this from the smallest deviations in how cosmic fields responded to cooling. As the universe expanded and cooled further, each phase transition imprinted information into space. Tiny quantum fluctuations stretched into macroscopic imprints during the rapid expansion of inflation. These variations were amplified into the seeds of the cosmic microwave background, patterns that satellites like WMAP and Planck would measure billions of years later with exquisite precision. The universe, in its earliest moments, was a stage where temperature dictated identity. When it was too hot, symmetry reigned and distinctions vanished. When it cooled, the structure emerged, not gradually, but suddenly, decisively, as if nature were flipping switches that determine everything that would come afterward. By the time the universe was minutes old, its major phase transitions were complete. The fields had chosen their states, the forces had separated, the first ingredients of structure had been planted. The universe was still young, chaotic, and unimaginably hot, but the fundamental groundwork was done. What remains is the story of how one specific symmetry breaking, the Higgs transition, changed everything by giving mass to the elementary particles themselves. Imagine the universe about a trillionth of a second after the Big Bang. The temperature is still fierce, tens of trillions of degrees, but cooling fast. The primordial plasma is dense with particles interacting so rapidly that no single entity can retain a stable identity for long. Among all the fields that fill space, one in particular is about to make a decision that will shape everything from the mass of the electron to the way stars burn. This is the moment of electroweak symmetry breaking, where the Higgs field chooses a side. To understand what that means, we need to briefly unpack what the electroweak force once was. Today, we treat electromagnetism and the weak nuclear force as two separate phenomena. Electromagnetism governs light, electric charge, circuits, chemistry. The weak interaction governs radioactive decay, the processes inside the sun that convert protons into neutrons, and the behavior of neutrinos. They feel distinct because they act differently, with different ranges, different strengths, and different mediating particles. But at extremely high energies, energies that permeated the early universe, these two forces merge into a single unified interaction, the electroweak force. Their separation is not fundamental. It emerges only when the universe cools enough for a particular field to adopt a non-zero value. That field is the Higgs field. Before the symmetry breaks, all particles interacting with the electroweak force behave as if they have no mass. The carriers of the weak force, particles we now call W and Z bosons, are massless. The photon is massless. The distinction between these particles does not yet exist. Everything that experiences electroweak interactions is interchangeable under specific transformations. This is what symmetry means in this context. The laws of physics look the same under certain rotations in the mathematical space that describes the interactions. But a perfectly symmetric system is fragile. As the universe cools, the Higgs field becomes unstable at its symmetric point. To picture this, physicists often introduce the metaphor of the Mexican hat potential. Imagine a sombrero-shaped surface, a tall bump at the center, surrounded by a circular valley. If a marble sits on the peak in the center, it is in a symmetric position, the same distance from every point on the valley floor. But that peak is unstable. A tiny nudge sends the marble rolling down into one side of the valley. The universe began with the Higgs field effectively balancing on the top of that central bump during high-energy conditions. Symmetry was maintained only because the extreme temperature smoothed the entire system, but as the universe expanded and cooled, the central peak reasserted itself. The symmetric state became unstable. The Higgs field fell into the valley, choosing a position, one among infinitely many equivalent ones, where the value of the field is no longer zero, and that single decision changes the identity of matter. When the Higgs field settles into that valley, it acquires what physicists call a vacuum expectation value, a baseline, persistent presence throughout the universe. It permeates every corner of space, providing resistance to particles that interact with it. The more strongly a particle couples to the Higgs field, the more mass it acquires. Mass, in this picture, is not simply an intrinsic property, it is a dynamical effect, the product of interaction with a universal field. Particles that couple strongly, like the top quark, become heavy. Particles with weaker couplings, like electrons, acquire smaller masses. Neutrinos, for reasons still not fully understood, interact so faintly that their masses remain almost negligible. Photons do not couple to the Higgs field at all, which is why light has no mass and can travel across the universe without slowing. The W and Z bosons, the carriers of the weak force, gain significant mass from their interactions with the Higgs field. This mass gives the weak interaction its extremely short range, limiting it to the scale of atomic nuclei. Meanwhile, the photon, immune to the Higgs mechanism, stays massless and becomes the carrier of the electromagnetic force. And just like that, electroweak symmetry is gone. Two distinct forces appear where once there was one. Their separation is not imposed by nature externally. It is a byproduct of the Higgs field selecting one of those valleys in the potential landscape. All of modern particle physics depends on this symmetry-breaking event. Without it, every particle we know would behave as if it were massless. Atoms would not form. Chemistry would collapse. Planets, stars, and life would be impossible. A universe without the Higgs field choosing a side would be a universe without structure. For decades, this idea remained theoretical, proposed through a handful of independent papers published in 1964. François Englert and Robert Brute described a mechanism by which gauge bosons could acquire mass while preserving mathematical consistency. Peter Higgs followed with a separate paper introducing what became known as the Higgs field, and briefly mentioning that such a mechanism implied a new particle, the Higgs boson. Two other groups, Guralnick, Hagen and Kibble, and independently Anderson, developed related ideas, contributing to the theoretical foundation. But the idea of a universal field giving mass to particles was radical. It solved a major problem in the electroweak theory, but it created a new challenge: how to verify it. From the mid-1970s onward, particle accelerators gradually confirmed the pieces of the electroweak framework. The W and Z bosons were discovered in 1983 at CERN's superproton synchrotron, providing stunning confirmation of the unified electroweak model developed by Glashow, Salam and Weinberg, work that earned the 1979 Nobel Prize. But the Higgs boson, the final missing piece, remained elusive. It required collision energies far beyond the capabilities of the accelerators of that era. The search stretched across decades and continents, culminating in the construction of the Large Hadron Collider beneath the French-Swiss border. With a circumference of 27 kilometers, about 17 miles. The LHC was designed specifically to find the Higgs boson and explore physics beyond the standard model. Its detectors, ATLAS and CMS, were engineered to sift through billions of proton-proton collisions each second, looking for rare signatures that would indicate the presence of a fleeting particle that decays almost immediately after being created. On July 4, 2012, after years of data collection and analysis, scientists at CERN announced the discovery of a new boson with a mass around 125 giga-electron volts. The signal appeared independently in both ATLAS and CMS, matching the predictions of a Higgs boson remarkably well. It was a scientific milestone comparable to the discovery of DNA's structure or the detection of gravitational waves, an achievement built on half a century of theoretical and experimental work. But perhaps the most profound part of the story is its simplicity. The Higgs boson is not what gives particles mass. It is merely the excitation, the ripple, of the Higgs field. What gives particles mass is the field's decision, made in the first instance of cosmic history, to settle into a non-zero value. The Higgs boson is the universe's way of letting us confirm that this field exists. When the Higgs field chose a side, it transformed a symmetric, massless universe into one capable of forming galaxies, stars, and the biochemical complexity that eventually led to life. A single shift in a field, a subtle change in energy configuration, created the conditions for everything we see. The universe, in its earliest fractions of a second, was an arena of perfect equations. Every form of matter had a mirror version, an antimatter counterpart equal in mass, but opposite in charge. According to the symmetries built into the laws of physics, matter and antimatter should have been created in equal amounts. When the Big Bang produced particles, it produced antiparticles too. When quarks appeared, antiquarks appeared. Electrons had positrons. Protons had antiprotons. In that perfectly symmetric scenario, the universe should have been a brief, brilliant spark that ended almost as soon as it began. Matter and antimatter would annihilate in pairs, converting their mass entirely into radiation. If nature had followed its simplest mathematical rules, the cosmos today would be nothing but an expanding sea of photons, cooling as it grows. No galaxies, no stars, no carbon or oxygen, no planets or chemistry, no life. And yet, here we are, living in a universe overwhelmingly made of matter, not antimatter. The imbalance is enormous. For roughly every 1 billion particles of antimatter, there were 1,000,000,001 particles of matter. Almost everything annihilated, but that tiny excess remained. That scrap of a symmetry, an imbalance at the level of 1 part in a billion, became everything. The galaxies, the stars, the hydrogen clouds, the rocky planets, the biological complexity that eventually learned to wonder how the imbalance ever occurred. The puzzle is hauntingly simple. Where did the extra matter come from? Why didn't perfect symmetry win? In 1967, Soviet physicist Andrei Sakharov confronted this problem head-on. If the early universe truly began in a symmetric state, then something must have violated that symmetry. Something must have tipped the scale ever so slightly toward matter. He proposed 3 conditions, now known as Sakharov's conditions, that any successful explanation must satisfy. The first is baryon number violation. A proton, a neutron, and the quarks inside them carry what physicists call baryon number, a bookkeeping variable that ensures the total amount of matter remains constant. In ordinary physics, baryon number is preserved, but if the universe is to generate more matter than antimatter, that number must occasionally change. Some processes must create matter without simultaneously creating matching antimatter, or destroy antimatter without destroying equal amounts of matter. Without baryon number violating reactions, the matter-antimatter balance would remain locked. The second requirement is C and CP violation. C stands for charge conjugation symmetry, the idea that swapping particles with their antiparticles should not change the physics. P stands for parity, flipping spatial coordinates like looking into a mirror. CP symmetry combines the two. replacing particles with mirror-image antiparticles. For the early universe to end up with more matter than antimatter, nature must violate CP symmetry. If matter and antimatter behave identically under all conditions, the imbalance can never emerge. Experiments have confirmed CP violation in the decays of kaons and B mesons, but not nearly enough to explain the cosmic asymmetry. Something deeper must have occurred. The third condition is departure from thermal equilibrium. In a perfectly balanced environment, processes that create asymmetry can be undone by reverse processes. But if the universe undergoes rapid change, such as cooling during expansion or experiencing phase transitions, then the symmetry-restoring reactions may no longer keep up. During these non-equilibrium windows, tiny imbalances can become permanent. These three ideas form the backbone of modern baryogenesis theory. They tell us what the universe must have done, but not exactly how it did it. One possibility is electroweak baryogenesis, a mechanism tied to the same electroweak symmetry breaking described earlier. During the Higgs transition, bubbles of the new phase might have formed in the early universe, expanding like boiling water. The boundaries of these bubbles could have hosted CP violating processes that favoured the production of matter over antimatter. If the electroweak phase transition had been first order, a violent, bubble-filled event, this mechanism could produce the needed asymmetry. Unfortunately, measurements of the Higgs boson suggest the transition was more gentle and continuous, likely too smooth to drive strong baryogenesis. Still, theories beyond the standard model can revive this idea by modifying the Higgs sector or introducing new particles. Another candidate is gut baryogenesis, rooted in hypothetical grand unified theories, GUTS, proposed in the 1970s and 1980s. These theories attempt to merge the strong, weak, and electromagnetic forces into a single unified force at extremely high energies. In many versions of GUT physics, super-heavy particles decay in ways that violate baryon number and break CP symmetry, naturally generating a matter excess. These particles would have existed only in the earliest moments of the universe, far beyond the reach of current accelerators. While elegant GUT baryogenesis has not been experimentally confirmed, and proton decay, a key prediction, has never been observed. A third possibility is leptogenesis, which begins not with baryons but with leptons, particles like electrons and neutrinos. Some theories propose that in the early universe, very heavy neutrinos, much heavier than the ones we observe today, decayed in ways that violated CP symmetry. These decays could create an excess of leptons over antileptons. Later, through interactions built into the standard model, part of that lepton asymmetry could be converted into a baryon asymmetry. Leptogenesis remains one of the most compelling ideas, especially because it naturally emerges in theories that explain why neutrinos have such tiny masses. Yet despite these frameworks, the actual mechanism remains unknown. We have theories that satisfy Sakharov's conditions, but no smoking gun. No laboratory experiment has reproduced the necessary imbalance. No observation has directly revealed the fingerprint of the asymmetry's origin. And strangely, the biggest missing piece may be one we should have seen if matter and antimatter had truly started out equal. Imagine the early universe filled with both in perfect balance. As soon as conditions cooled enough for stable particles to form, matter and antimatter should have annihilated in enormous quantities, producing a flash of gamma rays so intense it would leave an unmistakable signature woven into the cosmic microwave background. A universe that annihilated itself would carry traces of this catastrophe, patterns in the radiation, distortions in the early plasma, or pockets where annihilation continued longer than others. But no such signature exists. The cosmos is shockingly quiet about antimatter. We see no large regions of the universe made of it. Galaxies composed of antimatter would produce gamma rays at their boundaries where matter and antimatter meet. We see none. Space is not hiding half of creation. The imbalance was present from the start, not a late-stage development. This silence, this absence of the annihilation flash, tells us something profound. The universe never gave antimatter a fair fight. Some mechanism in the earliest instance tipped the scales from the beginning. A slight asymmetry, 1 part in a billion, was enough to decide the fate of the cosmos. Whatever process generated that imbalance left no visible trace except everything. Every atom in your body, every star burning, every planet orbiting, every chemical bond that makes biology possible. Matter won by a sliver, and in doing so, created a universe capable of remembering that victory. In a universe governed by elegant equations, symmetry feels like a promise. Whatever the laws allow for matter, they should allow equally for antimatter. Charge conjugation, or C-symmetry, tells us that if you replaced every particle with its antiparticle, swapping signs of electric charge, the physics should stay the same. P-symmetry, parity, tells us that flipping spatial coordinates, like looking at nature through a mirror, should also leave the rules intact. Combine the two, and you get CP symmetry, the idea that if you replace everything with its mirror image antimatter counterpart, the laws of nature should not change at all. If CP symmetry held perfectly, the universe would have produced equal amounts of matter and antimatter at its birth. Perfect pairs, perfect annihilation, no leftover matter, no galaxies, no stars, no chemistry, no carbon, no observers. But somewhere in the early universe, nature bent its own rules. The imbalance required to produce a matter-filled cosmos demands that CP symmetry must be broken. Matter and antimatter must behave differently in some fundamental way. The question is, where and how strongly? To see how strange and how subtle this asymmetry is, we have to travel to 1964, when an experiment in a basement laboratory at Brookhaven National Laboratory unexpectedly revealed a crack in the mirror. Physicists James Cronin and Val Fitch were studying kaons, short-lived particles produced in high-energy collisions. Kaons come in different varieties, including 2 neutral species that behave in a particularly interesting quantum way. According to the theory at the time, one of these neutral kaons, known as the long-lived kaon, should decay only into 3 pions, a decay mode that preserves CP symmetry. The other neutral kaon, the short-lived kaon, could decay into 2 pions, which violates CP symmetry. The long-lived kaon, by definition, was expected to respect CP symmetry completely. It should never decay into 2 pions. Never. But when Cronin and Fitch let kaons travel through a long vacuum tube and measured their decays far downstream, they found something astonishing. A tiny fraction of long-lived kaons decayed into 2 pions. The decays were rare, about 1 in 500, but they existed. That sliver of forbidden decay broke CP symmetry. Nature showed its hand. When the results were published, the impact was immediate and profound. A fundamental symmetry of the universe, one assumed to be ironclad, was not respected. The discovery earned Cronin and Fitch the 1980 Nobel Prize, and it opened a new chapter in particle physics. It was the first experimental demonstration that matter and antimatter are not treated equally by the laws governing quarks. But this raised a new question. Was this tiny violation in kaons enough to explain why matter dominates the universe? It wasn't even close. The CP violation observed in kaon decays is far too small, many orders of magnitude too small, to produce the matter-antimatter asymmetry we see in the cosmos. It was proof of principle, not a full explanation. The search for stronger CP violation continued. In the late 1990s and early 2000s, 2 massive experiments, Babar at Selassie in California and Bell at KEK in Japan, were constructed specifically to hunt for CP violation in another family of particles, B mesons. These heavier cousins of kaons contain a bottom quark paired with either an up, down, or strange quark. Their decays are more complex, with many channels where CP violation might appear. Both experiments recorded billions of B meson decays, and both found clear, unmistakable CP-violating effects. B mesons and their antiparticles decayed at different rates into specific final states, confirming a prediction made by physicists Makoto Kobayashi and Toshihide Masukawa in 1973. Their mathematical framework, known as the CKM matrix, explained how quark mixing could lead to CP violation. The discovery was monumental. It completed an essential part of the Standard Model and earned Kobayashi and Masukawa the 2008 Nobel Prize. Then came LHCb, the Large Hadron Colliders experiment dedicated to precision measurements of heavy flavor quarks. With huge data samples and exquisitely sensitive detectors, LHCb has revealed CP violation in multiple decay channels of B mesons, BS mesons, and charm mesons. It has even found hints of unexpected asymmetries not fully explained by the Standard Model. The evidence is overwhelming. CP violation exists. Matter and antimatter do not behave as mirror images. And yet, all this still falls short. The CP violation the Standard Model provides, through the CKM matrix, is far too weak. Even if you optimistically feed every allowed CP violating decay into early universe calculations, the asymmetry you get is tiny, about 1 billion times too small to explain why matter survived annihilation after the Big Bang. This is one of the most glaring mismatches between theory and observation in modern physics. The universe tells us one thing, matter dominates, and the Standard Model tells us something else, that CP violation is too feeble to account for that dominance. So, where is the missing CP violation hiding? One possibility is that it lives in the neutrino sector. Neutrinos, almost massless and notoriously shy, may carry their own kind of CP violation through mixing angles not yet fully measured. Projects like T2K, NOVA, and the upcoming June and Hyper Kamiokande experiments aim to determine whether neutrinos and antineutrinos oscillate differently as they change flavor. If strong CP violation exists among neutrinos, it could feed into leptogenesis, a mechanism where an asymmetry among leptons is later converted into a baryon asymmetry. Another possibility is that CP violation exists in entirely new physics, particles or forces not included in the Standard Model. Many extensions of the model introduce new sources of asymmetry. Heavy right-handed neutrinos, additional Higgs bosons, supersymmetric particles, or unknown interactions that might have operated only in the earliest instance of cosmic time. If the electro-weak phase transition had been more violent, a first-order transition with expanding bubbles of broken symmetry, its boundaries might have produced strong CP violation. But the observed Higgs mass suggests the transition was smooth, not bubble-filled. A deeper mystery lurks in quantum chromodynamics, the theory of the strong force. QCD allows, in principle, for a term that would cause dramatic CP violation. Yet experiments searching for a neutron electric dipole moment have found nothing. The strong force appears to respect CP symmetry almost perfectly. Why it does so is itself a puzzle, the strong CP problem, and some theories propose axions to restore symmetry. All these open questions suggest something profound. We have not yet found the true source of the universe's imbalance. The matter-dominated cosmos requires CP violation far stronger or occurring in environments far different from anything we have observed in laboratories. Somewhere, in the earliest microseconds, the laws of physics bent much more dramatically than particle accelerators have so far revealed. What Cronin and Fitch discovered in 1964 was the first hint. What Babar, Bell and LHCb uncovered were additional cracks. But the deep fault line, the symmetry-breaking event that tipped the universe toward matter, remains hidden. We know it happened. We live inside its aftermath. If you zoom into the heart of a proton, down through its cloud of gluons, past the 3 valence quarks, into the turbulent sea of virtual particles, nature becomes far more chaotic than the macro-scale world suggests. Quantum chromodynamics, or QCD, the theory of the strong interaction, is one of the most successful and mathematically elegant frameworks in all of physics. It explains how quarks bind into protons and neutrons, how these nucleons form atomic nuclei, and why nearly all the mass of ordinary matter, not the mass of the quarks themselves, but the binding energy of the strong force, comes from the churning vacuum inside those particles. Yet, QCD hides a deep and troubling mystery. According to its structure, the strong force should violate CP symmetry very strongly. There is nothing in the mathematics that prevents QCD from bending the rules of matter-antimatter symmetry in a way thousands or even millions of times more pronounced than anything seen in weak interactions. In fact, the theory almost demands it, but experiments say it doesn't. The strong force behaves as though it respects CP symmetry with near perfection, far more strictly than the weak force does, and far more strictly than the standard model expects. If QCD violated CP symmetry even slightly, we should be able to detect it in the properties of neutrons, specifically in the existence of something called an electric dipole moment. We have been searching for this moment for decades, and every time the experiments get more sensitive, the neutron continues to insist, "I am still symmetric." This tension is known as the strong CP problem, and solving it may require a new particle, one that could also explain the dark matter permeating the universe. To understand how such a mystery arises, we need to look closely at the structure of QCD. The strong interaction is governed by gluons, carriers of the color force. Unlike photons, which are electrically neutral, gluons themselves carry color charge, meaning they interact with each other directly. This self-interaction makes QCD extraordinarily rich, allowing quarks to be confined inside hadrons and preventing them from ever escaping as free particles. One quirk of QCD is that, mathematically, it allows for a term in its equations known as the theta term. This theta term connects electric and magnetic fields inside the strong force in a way that can violate CP symmetry. If theta is non-zero, even in extremely tiny amounts, the neutron should develop an electric dipole moment. Think of a dipole moment as a separation of positive and negative charge within a particle. A neutron is electrically neutral overall, but that doesn't mean its internal charge distribution must be perfectly symmetric. If CP symmetry is broken, the strong force could push the quarks slightly off-center, producing a tiny internal electrical lean. The neutron would become a sort of quantum bar magnet for electric fields, with one end slightly positive, the other slightly negative. The physics is subtle, but the consequences are not. A non-zero theta term produces a measurable electric dipole moment that experiments can detect. If theta were of order 1, a perfectly natural value, it would create a neutron dipole moment 1,000,000,000,000 times larger than current limits. So experimental results force theta to be incredibly small, less than about 10 to the minus 10, a number so tiny that many physicists consider it absurdly unnatural. Why should theta be zero or near zero? The standard model offers no reason. The mathematics doesn't prohibit large CP violation in the strong force. There is no symmetry that forces theta to vanish. And yet the neutron tells us it must be incredibly close to zero. This mismatch between theory and observation is the heart of the strong CP problem. The search for the neutron electric dipole moment began in the 1950s. Early experiments were crude by modern standards. Equipment was often so sensitive that even nearby elevators or passing cars contaminated the readings. But as techniques improved, utilizing ultra-cold neutrons, superconducting magnetic shielding, and exquisitely stable fields, physicists kept pushing the upper limit lower. No dipole moment was found. By the 1990s and 2000s, limits improved by orders of magnitude. Neutrons were stored in magnetic bottles. Exotic materials were used to stabilize electric fields. Systematic errors were hunted down with increasing precision. Still nothing. Today, cutting-edge experiments like those at the Paul Scherrer Institute in Switzerland and the NEDM collaboration continue to push the sensitivity even further. If a neutron electric dipole moment exists, it must be smaller than 3 × 10 to the minus 26 electron centimeters, the current experimental upper bound. That's an astonishing level of precision. Scientists are detecting charge distributions within a particle to a fraction of a trillionth of a centimeter, and the neutron keeps refusing to tilt. This is not merely a matter of experimental patience. If theta is forced to be essentially zero, it suggests something deeper. Maybe the universe has some hidden mechanism that naturally drives theta towards zero. This is where one of the most elegant and influential ideas in modern theoretical physics emerges. In 1977, Roberto Peccei and Helen Quinn proposed a new symmetry, the Peccei-Quinn symmetry, that when broken, dynamically drives theta to zero. Their theory didn't just eliminate the strong CP problem, it predicted the existence of a new, very light particle, the axion. The axion, named after a brand of laundry detergent because it cleaned up the CP violation problem, is one of the most compelling hypothetical particles ever proposed. It is incredibly light, interacts extremely weakly with ordinary matter, and arises naturally from the Peccei-Quinn mechanism. If the symmetry is real and broke in the early universe, axions would have been produced in enormous quantities, so many that they could account for all of the dark matter in the cosmos. This dual purpose makes axions especially appealing. They don't just solve a deep theoretical inconsistency in QCD, they may also fill a major observational gap in cosmology. Searching for axions, however, is exceptionally challenging. Their interactions with photons and matter are so feeble that detecting them requires exotic technologies. Some experiments use magnetic fields to try to convert axions into detectable photons, a concept known as the axion haloscope, pioneered by the Adamax experiment. Others use resonant microwave cavities, cryogenic detectors, or even experiments with nuclear magnetic resonance that look for tiny oscillations caused by an axion field permeating space. Still others, like CAST at CERN, aim to detect axions streaming from the Sun. There are also astrophysical constraints. If axions existed with certain properties, they would affect the cooling of stars or supernovae in measurable ways. These limits help narrow the possible mass range and interaction strengths of the hypothetical particle. Despite decades of increasingly sensitive searches, no axion has yet been detected, but this is not discouraging. The allowed parameter space for axions is vast, stretching across many orders of magnitude in mass and coupling strength. Much of that space remains unexplored. The strong CP problem is a rare kind of puzzle in physics, one with enormous stakes. If we find the neutron electric dipole moment, it tells us that CP violation in QCD exists, and it opens a new chapter in understanding the early universe. If we instead confirm that the dipole moment is truly zero because of axions or another symmetry-restoring mechanism, then we uncover a new, fundamental symmetry of nature. Either outcome reshapes physics. Meanwhile, the search continues with growing urgency. Experiments around the world, PSI, SNS, NEDM at SNS, TUCAN in Canada, and future European collaborations aim to improve sensitivity by another order of magnitude or more. At those thresholds, the absence of a neutron dipole moment would strengthen the case for axions dramatically. But the implications go beyond particle physics. If axions exist and form dark matter, then their presence subtly affects the motion of stars in galaxies, the formation of cosmic structure, and even the oscillations of atoms on Earth. Some theories suggest that the axion field is not static, but oscillates at a frequency determined by its mass. If so, atoms and nuclei in precision experiments should oscillate too, creating a new frontier of tabletop dark matter detection. In this sense, the strong CP problem sits at the intersection of the very small and the very large. The behavior of quarks deep inside neutrons might reveal the identity of the invisible matter shaping galaxies. And underpinning all of this is a simple but profound question. Why is the universe so symmetric when it doesn't have to be? The strong force allows CP violation, the mathematics welcomes it, the standard model expects it, but the neutron remains silent, balanced, unpolarized. Either nature hides a mechanism we haven't discovered, or QCD conceals a piece of physics beyond the standard model, a piece that could rewrite our understanding of the cosmos. The missing electric dipole moment isn't just a null result, it's a doorway. Behind it may lie axions, new symmetries, or entirely new sectors of physics. The strong force, normally the most overwhelming of all interactions, may also be the most quietly revealing, pointing not through what it does, but through what it refuses to do. And somewhere in that refusal lies a clue to how the universe handled symmetry, how it decided which rules to keep and which to bend, and why matter, rather than mirror-symmetric nothingness, fills the sky. As the universe expands, its temperature falls, and with each drop, the fabric of reality becomes more differentiated. Forces that were once indistinguishable begin to specialize. Fields that were once unified begin to choose particular configurations. Symmetry, so dominant in the earliest instance, starts to fracture. What emerges is a universe whose laws are not simply given but sculpted, shaped step by cooling, like molten metal settling into crystalline form. This idea, forces separating as the universe cools, is not just a metaphor. It is the central principle behind spontaneous symmetry breaking, a phenomenon that physicists now view as one of the deepest organizing rules of nature. In the same way that water freezes into ice or iron becomes magnetized when it cools, the universe itself transitioned through a series of crystallizations, each one defining the behavior of its fundamental interactions. Today, we live with 4 fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. But in the first slices of a second after the Big Bang, these forces did not exist in the forms we know. Instead, they were woven together into unified interactions that only later separated, first gravity from everything else, then the strong force, and finally the electro-weak force dividing into the electromagnetic and weak interactions. The earliest of these breakings occurred at energies far beyond anything achievable in laboratories. Gravity, which today seems absurdly weak compared to other forces, was once comparable in strength when the universe was small enough and hot enough. As space expanded, gravity decoupled first, becoming effectively distinct, while the remaining forces stayed unified. Next came the separation of the strong force. According to many versions of grand unified theories, gut models, the strong interaction, electromagnetism, and the weak interaction were once part of a single, more symmetrical force. At temperatures around 10 to the 29th Kelvin, corresponding to about 10 to the minus 36th seconds after the Big Bang, that symmetry should have shattered. The strong force crystallized out like the first solid structure in the early universe's cooling melt, leaving electromagnetism and the weak interaction still unified. The energy scales involved are unfathomably high, and we have no direct experimental access to them. But the mathematics of gut models suggests that the matter particles we know, quarks and leptons, once existed as different states of a single unified field. The breaking of the unified force into the strong and electroweak forces would have been as profound as the splitting of a beam of light into colours. Electroweak symmetry breaking, driven by the Higgs field, came much later at temperatures around 10 to the 15th Kelvin and a cosmic age of roughly 10 to the minus 12th seconds. This breaking gave mass to the W and Z bosons, distinguishing the weak interaction from electromagnetism and locking in the structure of physics as we know it. Each of these transitions is a moment where the universe chose a specific state among many possibilities, a reduction of symmetry that created something new. The mathematical structures underlying gut models often contained large symmetric groups, such as SU of 5, SO of 10, or E6. These represent highly unified forms of reality that fracture into smaller subgroups as the universe cools. Each fracture point corresponds to a rearrangement of fields, particle properties, and interactions. This is why cosmic cooling is analogous to crystallization. A perfect liquid, cooled very slowly, may settle into one of many possible crystal patterns. The final structure depends on tiny fluctuations, random imperfections, and stability conditions that emerge only as temperature drops. The universe behaved the same way, settling into a particular arrangement of forces and particle properties that allowed matter to exist. One of the most intriguing predictions of gut models is the existence of magnetic monopoles, particles that carry isolated north or south magnetic charge. In ordinary magnets, north and south poles always come in pairs. Break a magnet in half and each piece still has both poles. But gut symmetries naturally produce monopoles during symmetry-breaking transitions, in the same way that defects appear when crystals form. These monopoles would have been produced in enormous numbers during the strong electro-weak separation, created as topological defects in the fields that filled the early universe. If monopoles had formed as expected, they would still exist today. They should be massive, stable, and incredibly energetic, relics of the universe's earliest symmetry breakings. Their detection would revolutionize physics. It would confirm gut models, illuminate how forces unified, and help explain the fine structure of cosmic evolution. But we haven't found them. Not in cosmic ray detectors, not in geological samples, not in deep underground experiments, not in searches conducted across decades and continents. The apparent absence of monopoles is so striking that it contributed to one of the most influential ideas in modern cosmology: inflation. When Alan Guth proposed cosmic inflation in 1980, one of the problems it addressed was the monopole problem. If the universe expanded exponentially fast during a tiny fraction of a second, any monopoles formed before inflation would be diluted to near invisibility. Instead of being abundant, they would be spread so thinly that finding even one would be extraordinarily unlikely. Inflation solved more than the monopole problem, such as the flatness and horizon problems, but this dilution was one of its earliest triumphs. Without it, gut models would predict far more monopoles than we observe. But the absence of monopoles doesn't mean they do not exist. Some gut models predict fewer monopoles. Others suggest that their masses are so enormous, possibly 10 to the 16th power times that of a proton, that even inflation may not dilute them completely, and that they remain detectable with the right instruments. Experiments like moody macroscopic detectors searching for catalyzed proton decay and analyses of cosmic magnetic fields all attempt to find indirect evidence of monopoles. The search continues, because discovering even one monopole would answer deep questions about how forces separated at the dawn of time. As we step back and consider the big picture, a pattern emerges. The expansion of the universe was not merely a stretching of space, it was a cooling process that allowed hidden layers of physics to reveal themselves. The universe did not begin with electromagnetism, or the weak interaction, or the strong interaction. It began with a higher symmetry that gradually fractured, like superheated glass cracking into distinct shards. This fracturing is the essence of spontaneous symmetry breaking. Nothing external forced the universe to adopt its current laws. Instead, those laws crystallized out of the cooling cosmic plasma, encoded by the ways fields settled into their lowest energy states. The forms of matter, the strengths of forces, and the properties of particles were not preordained. They were consequences of the cosmos choosing a particular path through an immense landscape of possibilities. If the early universe had cooled differently, or settled into a different minimum of the field potential, Physics itself would be different. Atoms might not exist, stars might not form, the weak interaction might not operate, chemistry might not unfold. In some branches of theoretical exploration, universes with different symmetry breakings are considered entirely separate realities in the multiverse landscape. What we experience today, gravity moulding galaxies, electromagnetism governing atoms, the strong force binding nuclei, is the final product of a long sequence of cosmic phase transitions. Each crystallization reduced symmetry and increased structure. Each reduction transformed the universe from abstraction into complexity. Each shift brought the laws of nature closer to the ones we now rely on to explain everything from quarks to quasars. And in the cosmic background of symmetry breaking lies a persistent theme. When the universe cools, it reveals itself. If you look up at the night sky, the universe appears filled with structure. Galaxies arranged in filaments stretching across billions of light years, clusters bound together by gravity, stars burning in spirals and ellipticals, planets orbiting quietly in the gravitational wells of suns. None of this complexity could exist in a universe that remained perfectly symmetric. Absolute symmetry is sterile. It erases contrast, suppresses growth, and leaves no room for gravitational clumping. A perfectly uniform cosmos would expand forever as a smooth, featureless fog of particles and radiation. The existence of structure means something fundamental must have broken that symmetry. The universe had to deviate from perfection, slightly, subtly, but decisively. What's remarkable is how small those deviations were. The entire cosmic web owes its existence to fluctuations in density of about 1 part in 100,000. These tiny seeds, present when the universe was only about 380,000 years old, were enough for gravity to begin amplifying small differences. Over billions of years, those differences became galaxies, stars, and planets, and eventually observers capable of studying the imperfections that made their existence possible. But where did those first asymmetries come from? The answer lies deep in the early universe, in the smallest quantum jitters of fields that filled all of space. During the epoch of inflation, a period of exponentially rapid expansion, the cosmos stretched these fluctuations from subatomic scales to cosmic scales, imprinting them across the universe like faint fingerprints. What began as tiny quantum noise became the blueprint of all large-scale structure. Quantum fluctuations are unavoidable. They arise from the uncertainty principle itself, which tells us that fields cannot remain perfectly still. Even in a vacuum, fields tremble. Particles flicker in and out of existence. Energy fluctuates in tiny, spontaneous bursts. These deviations are minuscule, usually confined to scales far too small to matter in everyday physics. But inflation changes everything. In the first tiny fraction of a second after the Big Bang, the universe is believed to have undergone a period of exponential expansion. A region smaller than a proton ballooned to a size far larger than the observable universe. This stretching did something extraordinary. It took those quantum fluctuations, microscopic irregularities in fields and energy density, and expanded them to macroscopic scales. What was once subatomic became astrophysical. Imagine painting a canvas with a brush so fine that no one can see the strokes. Then imagine stretching the canvas billions of times until the brush texture becomes visible. Inflation did exactly that. It magnified the unseeable. These fluctuations became slight variations in the density of matter and radiation. Some regions ended up with slightly more material, others slightly less. After inflation ended, the universe continued expanding, cooling, and transitioning from an opaque plasma to a transparent gas. When photons finally decoupled from matter at around 380,000 years, the moment captured by the cosmic microwave background, or CMB, these density differences became imprinted as temperature variations. Slightly overdense regions appeared as cooler spots, because photons had to climb out of deeper gravitational wells. Slightly underdense regions appeared as warmer spots. The CMB is the oldest image of the universe we have. It is, in essence, a photograph of broken symmetry. Galaxies, stars and planets formed through gravitational collapse. But gravity can only amplify what already exists. It cannot create initial differences, it can only enhance them. If the early universe had been perfectly smooth, gravity would have had nothing to work with. No region would have been denser than any other. Collapsing structures would never begin. The universe would remain forever uniform, expanding without forming anything. This is why symmetry breaking is the engine of cosmic architecture. Every galaxy owes its origin to a slight excess in density. Every star exists because one pocket of gas was minutely heavier than the surrounding region. Every planet forms because turbulence and collapse continued at smaller scales. The complexity of the cosmos begins with a symmetry. The structure requires imperfection. The cosmic microwave background allows us to see these imperfections directly. When satellites like WMAP, launched in 2001, and later Planck, launched in 2009, mapped the temperature of the sky in microwaves, they found a nearly uniform background. A perfect glow at about 2.7 Kelvin, but with tiny deviations. These variations are incredibly small, about 0.00003 Kelvin, and yet these faint patterns contain almost everything we know about the early universe. The WMAP spacecraft provided the first high-precision full-sky maps of the CMB, showing a characteristic spectrum of temperature fluctuations that match almost exactly what inflation predicts. The peaks and troughs in the angular power spectrum, the statistical distribution of these fluctuations at different scales, give us information about the density of matter, the amount of dark matter, the geometry of the universe, and the physics of the early plasma. Then Planck refined everything. With higher resolution and sensitivity, Planck revealed the CMB in unprecedented detail. It showed slightly sharper peaks, more accurate measurements of polarization patterns, and subtle anomalies that continue to puzzle cosmologists. But the essential picture remained. The universe began with tiny asymmetries seeded by quantum fluctuations and stretched by inflation. The patterns measured by Planck and WMAP are not random, they match a nearly scale-invariant distribution, meaning fluctuations at different sizes follow a predictable pattern. This is exactly what inflationary models predict. Moreover, the uniformity of the CMB across the entire sky, regions too far apart to have communicated with each other through light, would be impossible without inflation smoothing the universe before stretching it. The CMB also allows us to see something profound. The universe carries memory, it remembers its imperfections. The density variations recorded in the CMB are the direct ancestors of the cosmic web we see today. Where the CMB has slightly colder, denser spots, we find clusters and superclusters. Where it has slightly warmer, less dense regions, we find voids, vast expanses with few galaxies. Symmetry breaking is not merely an abstract principle, it is written into the sky. The CMB maps show that the early universe was astonishingly uniform, yet not perfectly so. The variations were small but crucial. If the fluctuations had been slightly weaker, say 1 part in 1 million instead of 1 part in 100,000, gravity would not have been strong enough to form galaxies. If they had been slightly stronger, say 1 part in 10,000, the universe would have collapsed into black holes and dense clumps, leaving no room for stable, long-lived stars. The balance is astonishingly fine. The right amount of disorder is needed to make order possible. One of the most compelling parts of this story is that the symmetry breaking is spontaneous. Nothing forced the fluctuations to take the precise values they did. Quantum fields were jittering, inflation expanded space, and the resulting density pattern emerged as a natural consequence of probabilistic physics. The universe did not need to be designed to produce galaxies, it merely needed to be imperfect. These imperfections also appear in polarization patterns of the CMB. specifically the E-mode polarization detected cleanly by Planck. These polarization maps give us a second view of the same story, confirming that the temperature fluctuations are not artifacts, but genuine signatures of density variations in the early plasma. Searches for B-mode polarization, which would be a direct signature of gravitational waves generated during inflation, are ongoing with experiments like BICEP and future missions such as LIGHTBIRD. As cosmologists study these fluctuations, they gain insight into physics far beyond the reach of particle accelerators. Inflation operates at energies trillions of times higher than those achievable by the LHC. The CMB becomes a kind of particle physics observatory written across the sky, allowing us to probe the structure of fields that shaped the newborn universe. But everything returns to a simple truth. Structure requires broken symmetry. The universe has complexity because it refused perfection. The cosmic microwave background is the fossil of that refusal. It is a delicate pattern of warm and cool regions, the first visible sign that symmetry had fractured and that the universe had chosen a path toward complexity. From those tiny variations, gravity built the cosmic web. Galaxies condensed, stars ignited, planets formed from leftover disks of dust and gas. Chemistry emerged in the hearts of stars and the atmospheres of young worlds. Life became possible because the cosmos is not perfectly balanced. In the end, the vast architecture of the universe, the filaments, the voids, the spirals, the clusters, is nothing more than amplified imperfection. And the CMB lets us see the moment it all began. Life, despite its tendency toward order and repetition, is built on a fundamental violation of symmetry. Every protein in every cell of every organism on Earth is constructed from the same class of building blocks, left-handed amino acids. The sugars in nucleic acids, meanwhile, are all right-handed. This selective use of one-handedness, or chirality, is one of the most striking asymmetries in biology. It is also one of the deepest mysteries in the origins of life. Chemically, there is no obvious reason for this uniformity. Amino acids synthesized in laboratories, through spark discharge experiments, ultraviolet irradiation, or reactions in interstellar ice analogues, always produce equal mixtures of left and right-handed molecules. These are called racemic mixtures. They are perfectly symmetric. Nothing favours one side over the other, but biology does. The entire molecular foundation of life depends on this symmetry breaking. Proteins built from a racemic mixture would not fold into stable structures. They would produce tangled, dysfunctional chains. Likewise, the double helix of DNA, its graceful twist, its replication fidelity, requires uniform molecular handedness. Break the symmetry, and life becomes possible. Keep the symmetry, and life cannot begin. This raises a profound question: why did life choose one hand? And why that hand? To trace this story, we return to the 19th century, when a young French scientist named Louis Pasteur noticed something strange in crystals of tartaric acid. Some crystals rotated polarized light to the left, others rotated it to the right. But when he examined samples derived from biological sources, specifically wine fermentation, he found they only rotated light in one direction. Pasteur realized he was seeing a difference in molecular handedness long before the full structure of molecules was understood. He painstakingly separated left and right-handed crystals with tweezers, an act of scientific patience rarely matched, demonstrating that molecules could exist as mirror images of each other. More remarkably, he discovered that living organisms preferred one of these mirror forms, a preference not shared by non-biological processes. This was the first evidence that life is chiral, that it chooses sides. Pasteur saw chirality as a sign of life's influence. The modern view is more nuanced. Life's handedness may have emerged long before biology existed, encoded in the prebiotic chemistry of early Earth, or even seeded through cosmic processes that unfolded in interstellar clouds and meteorites. But regardless of the origin, the significance is clear. Chirality is a form of symmetry breaking essential for biological complexity. Consider the role of amino acids. A protein is a sequence of amino acids folded into a precise three-dimensional shape. That shape determines the protein's function. Enzymes, receptors, structural proteins all depend on exact folding. Use right-handed amino acids instead of left-handed ones, and the protein falls apart. Use a 50-50 mixture, and the protein cannot form at all. Life as we know it requires the consistent choice of the same handedness for every amino acid in every protein. Where could this preference have arisen? One possibility is cosmic. Meteorites, such as the Murchison meteorite, contain amino acids with slight excesses of left-handed forms. These meteorites date back over 4.5 billion years and preserve chemical processes from before Earth had oceans. The fact that some show chiral biases hints that cosmic radiation, polarized starlight, or chemical reactions on asteroid surfaces may have nudged the balance slightly away from symmetry. Even a tiny initial bias, once amplified by self-replicating reactions, could have become locked into biology. Polarized ultraviolet light is particularly compelling. Regions near massive stars produce circularly polarized radiation. If such light preferentially destroys one mirror form of amino acids more than the other, an asymmetric mixture could emerge. Over time, these molecules might accumulate on dust grains, become integrated into asteroids, and eventually fall into young planets. Another possibility is geological. Early Earth was rich in minerals capable of catalyzing reactions on crystal surfaces. Certain minerals, such as some forms of calcite, naturally present chiral surfaces. Molecules binding to them could adopt preferential orientations, slightly biasing chemical reactions toward one-handedness. Even a small bias could matter. In autocatalytic systems, chemical networks where products help produce more of themselves, a tiny initial asymmetry can dominate as the system evolves. The classic example is the SOI reaction, a laboratory process discovered in the 1990s. In this reaction, a small initial chiral imbalance, even 1 part in a trillion, is enough to produce almost entirely one-handed products after several iterations. The reaction amplifies chirality dramatically. If similar autocatalytic processes operated on early Earth, they could have taken a tiny initial asymmetry and transformed it into a universal feature of prebiotic chemistry. Yet another possibility involves parity violation in the weak interaction. The weak force, unlike gravity or electromagnetism, already violates mirror symmetry. It treats left-handed particles differently from right-handed ones. Some theorists have explored whether weak interaction physics could induce small energy differences between left and right-handed molecules. The predicted difference is tiny, far too small to dominate chemical reactions directly, but over geological or cosmic timescales, even such a small bias could influence prebiotic chemistry. The truth is likely a combination of factors: cosmic irradiation, mineral surfaces, autocatalytic amplification, and the inherent asymmetry of the weak force may all have played roles. What matters is that somewhere, somehow, symmetry broke. Left beat right. A decision was made, not by intention, but by chemistry, that set the stage for everything that followed. The consequences of that decision are enormous. Once life chose left-handed amino acids, it became locked in. Proteins built from left-handed amino acids interact with DNA and RNA in highly specific ways. Cellular machinery evolved to recognize only one orientation. Ribosomes translate sequences with strict chiral sensitivity. Enzymes fold and bind to substrates in chiral-specific pockets. If a right-handed amino acid enters a biological system, it is treated as a foreign contaminant. Many poisons work by exploiting this mismatch. Molecules with the wrong chirality bind incorrectly, disrupting biochemical pathways. The asymmetry is so fundamental that some scientists argue chirality might be a universal requirement for life. Any system capable of controlled replication and metabolism needs molecules that can fold, align, and copy themselves reliably. That reliability requires uniform handedness. Even alien biochemistries, whether carbon-based or built on entirely different chemical platforms, may need to break symmetry in order to achieve complexity. Chirality also gives direction to biology. DNA's helix twists consistently in one direction. Motor proteins, such as myosin and kinesin, walk along cellular filaments that spiral in defined orientations. Even large-scale organisms exhibit a symmetry. Human hearts on the left side, snail shells coiling in specific directions, plant vines spiraling consistently. These are echoes of a symmetry breaking that began with molecules. If early Earth had chosen right-handed amino acids instead, life might still have emerged, but it would be chemically incompatible with life as we know it. Two worlds could coexist, each with its own chirality, unable to exchange proteins or genetic material. Some science fiction stories imagine such mirror life, but on Earth only one choice took hold. Why that choice? Perhaps it was chance. Perhaps it was cosmic. Perhaps physics itself nudges chemistry toward one direction. What's certain is this: biological symmetry breaking is not an accident. It is a prerequisite. Life refuses to be even, and because of that refusal, the world is filled with structure. Every cell, every protein, every strand of DNA carries the memory of a decision made long before biology existed. The universe's earliest symmetry breakings created galaxies, stars, and planets. This later biochemical breaking created metabolism, replication, and evolution. The cosmos requires imperfection to build structure. Life requires it to build itself. Even now, billions of years after the universe's earliest fractures, physicists continue to search for the faint echoes of symmetry breaking. The cosmos we see today, its structure, its particles, its laws, suggests that the universe once obeyed deeper, more unified principles. We detect their traces not in what is present, but in what is missing. Interactions that should exist but do not. Symmetries that appear partial. Particles that have mass when theory suggests they shouldn't. Forces that look like fragments of something larger. To uncover these hidden layers, scientists build vast machines. Subterranean caverns holding giant water tanks, tunnels 27 kilometers long, detectors sensitive enough to catch a single neutrino passing unseen through matter. These experiments are monuments not just to engineering, but to an idea: the belief that the universe still hides imperfections that reveal its past. The largest of these machines is the LHC, the Large Hadron Collider near Geneva. Beneath the French-Swiss border, protons circulate in opposite directions at nearly the speed of light, guided by superconducting magnets colder than outer space. When they collide, the energy compressed into a tiny point briefly recreates conditions similar to those of the early universe. Temperatures high enough to shatter symmetries, energy densities intense enough to form exotic particles. The discovery of the Higgs boson in 2012 confirmed one kind of symmetry breaking. But the LHC's deeper mission continues, searching for new physics beyond the standard model. Many theories predict that the Higgs sector is not alone, that hidden symmetries could manifest as supersymmetric partners, heavy W' or Z' bosons, or particles carrying new quantum numbers. None have been found yet, but the exploration continues with upgraded detectors and higher luminosities. The LHC also plays a role in one of the most delicate symmetry tests in physics, the hunt for electric dipole moments in elementary particles. While the neutron electric dipole moment is primarily measured in dedicated tabletop experiments, the LHC provides complementary searches through its studies of CP violation in heavy flavor decays. These measurements probe whether quarks behave differently from antiquarks, and whether that difference evolves with energy. Any departure from standard model predictions could point to new sources of CP violation, sources strong enough to explain the matter-antimatter asymmetry of the universe. But not all symmetry breaking can be revealed at high energies. Some require us to look deep underground, into immense detectors shielded from cosmic noise. In the mountains of Japan, the Super Kamiokande experiment, SUPERC, sits inside a cavern filled with 50,000 tons of ultra-pure water. Thousands of photomultiplier tubes line the walls, waiting for the faint blue flash of Cherenkov radiation produced by a neutrino interacting with a water molecule. SUPERC has transformed our understanding of neutrinos, offering some of the first clear evidence that they change flavor as they travel, a discovery that itself implies mass, a form of symmetry breaking not included in the original Standard Model. Neutrino oscillations are a gateway to one of physics' most urgent questions. Do neutrinos violate CP symmetry? If neutrinos and antineutrinos oscillate differently, the universe may contain a hidden source of CP violation powerful enough to explain baryogenesis. Detecting this would reveal not just a broken symmetry, but the mechanism that tipped the cosmic balance toward matter. To pursue this possibility with greater precision, 2 next-generation experiments are underway. June, Deep Underground Neutrino Experiment in the United States, and Hyper Kamiokande in Japan. June will fire an intense neutrino beam from Fermilab across 1,300 kilometers, about 810 miles, of Earth's crust to a cavern of liquid argon tanks in South Dakota. Hyper Kamiokande will expand the SUPERC design, building an even larger water Cherenkov detector with vastly improved sensitivity. Both experiments aim to determine whether neutrinos and antineutrinos behave differently in their oscillations. Even a slight difference, an asymmetry of a few percent, would represent one of the most significant symmetry breakings ever observed. It could directly connect the physics of the early universe to the existence of matter today. Other underground experiments hunt for an even more dramatic sign of broken symmetry: proton decay. Grand unified theories such as SU5 or SO10 predict that protons, though extraordinarily long-lived, are not perfectly stable. Their decay would signal that the strong, weak, and electromagnetic forces were once unified. It would be direct evidence of a symmetry so profound it lies entirely beyond the reach of current accelerators. So far, no proton decay has been seen. Detectors like SUPERC have observed nothing but silence, placing lower bounds on the proton lifetime above 10 to the 34th years. If protons do decay, the universe is far more symmetric at high energies than at low, and that symmetry was shattered as the cosmos cooled. Hyper Kamiokande and other future detectors will push sensitivity even higher, searching for rare events that may occur only once per universe-sized volume per year. Meanwhile, tabletop precision experiments continue the search for electric dipole moments in electrons, neutrons, and even atoms. These searches probe symmetries with extraordinary sensitivity, equivalent to measuring a shift smaller than a fraction of a proton's diameter across the width of a continent. If an electric dipole moment is found, it would reveal that CP symmetry breaks at levels the Standard Model cannot explain, an unmistakable sign of new physics. This mosaic of experiments, LHC, SUPER-K, June, Hyper Kamiokande, proton decay searches, EDM measurements, is unified by a single theme. Modern physics expects deeper symmetries beneath what we observe. The Standard Model is successful, precise and predictive, but incomplete. It does not explain why neutrinos have mass. It does not explain dark matter. It does not unify gravity with the other forces. It cannot account for baryogenesis. It allows strong CP violation that does not occur. It contains many parameters that seem arbitrary, masses, mixing angles, coupling constants, that hint at a more natural, more symmetrical underlying structure. The universe we observe appears asymmetric not because symmetry is absent, but because symmetry has been broken. The fundamental question becomes, what symmetries existed before the breaking? Some theorists imagine supersymmetry, a symmetry between fermions and bosons. Others investigate grand unification, where forces merge into a higher SU5 or SO10 symmetry. Still others consider deeper mathematical structures like E6 or hidden sectors interacting only faintly with ordinary matter. Even more radical models explore extra spatial dimensions where symmetry appears broken only because we see a limited projection of a larger reality. In every case, symmetry breaking becomes the key. When a deep symmetry shatters, the fragments resemble the forces and particles we observe today. The more fragments we identify, the clearer the original symmetry becomes. Symmetry breaking is not a flaw in nature. It is a roadmap. Each crack points towards something larger. Each deviation hints at a deeper rule. Each asymmetry tells us that we have not reached the foundation yet. The experiments of today, those buried in mountains, submerged in water, cooled to near absolute zero, or accelerating particles around subterranean rings, are all attempts to map these cracks. They look for the imbalances, the forbidden decays, the rare oscillations, the impossible electric dipoles, because somewhere within these imperfections lies the next chapter of physics. We know the universe broke its early symmetries to create matter, structure, and life. Now we search for the next break, the one that will reveal what came before. If you imagine a universe that never broke symmetry, it becomes something almost eerie, perfectly smooth, perfectly uniform. No galaxies, no stars, no matter clumping anywhere, just an expanding wash of light and particles, all identical, all evenly spread, all behaving in precisely the same way. It would be tidy, predictable, and utterly empty. Perfection at the cosmic scale does not mean richness. It means sameness. It means nothing ever stands out enough to grow into something more. In a universe without broken symmetry, gravity has no foothold, chemistry has no asymmetry to build on, and quantum fluctuations never stretch into the seeds of structure. The laws might be elegant, but the outcome would be silence. The universe we inhabit chose a different path. It allowed a slight tilt, a tiny imbalance, a small deviation from perfection. And in that deviation, everything began. Once symmetry shattered, first in the separation of forces, then in the mass of particles, then in the imbalance between matter and antimatter, the universe gained contrast. Empty space acquired texture. Fields rolled into new configurations. Density ripples grew into filaments of galaxies. What had been a smooth vacuum became a landscape of stars, planets, oceans, atmospheres, and eventually minds capable of contemplating how it all happened. It's strange to think that the atoms in your body exist because the Higgs field did not stay balanced, because quantum fluctuations refused to cancel, because baryogenesis favoured matter by the slightest fraction. Each of these breakings was tiny, almost reluctant. Yet together they transformed an undifferentiated early universe into one with complexity layered on top of complexity. Imperfection, rather than flaw, became possibility. Symmetry breaking became creativity. Even at the biological level, the same theme repeats. Life chose one-handedness for its molecules, one direction for its spirals, one orientation for its proteins. That small decision, left instead of right, allowed DNA to twist, enzymes to fold, and organisms to evolve. Without breaking molecular symmetry, biology would be as barren as a perfectly uniform cosmos. As you imagine yourself sitting near a quiet fireplace, listening to the gentle crackle of burning wood, it becomes easy to feel the scale of this story shrink back down to something personal. Every spark rising from the flame, every warm glow on the wall, every breath of air you take is made of particles that owe their existence to ancient asymmetries. You are literally built from the universe's refusal to be perfect. The beauty of it is subtle. The universe did not become rich by striving for complexity. It became rich by allowing imperfection, by letting symmetry break, by leaning ever so slightly toward imbalance. A perfectly symmetrical universe would have no story to tell, Ours tells a story in every star, every element, every cell. The cosmos chose not to remain flawless, and in that choice it became alive.